So software sustainment, it generally consumes 65 to 75% of total ownership cost for complex software systems, and yet it's generally overlooked during software estimation and supported by limited data sets. And I know ISBSG has one of the most comprehensive data sets for software maintenance and support that's available to commercial industries. I know the US government has data sets as well. But today I'm going to talk about research that I did looking into the ISBSG software maintenance and support data set. This is a, what's the word I want to use? It's a compressed version of the study that I did because I have 25 minutes, not an hour. There is, however, available to anyone who on the last slide, my contact information is available. And if anyone would like to see the entire paper, I'm more than happy to share that with you. So what we're going to talk about today, lessons learned from the ISBSG M&S data set. So a little bit of introduction, then we'll talk about the lessons to be learned, the learning process, and what are the results and the lessons that we actually learned during this process. So as I mentioned earlier, software sustainment is an increasingly important part of the operation of complex software systems. 65 to 75% is the amount touted. Some projects take more than that, and especially with, I do a lot of work with government systems, DoD, and government contractors, and their software systems sometimes stay way longer into maintenance than originally anticipated. Software estimates continue to focus primarily on development costs, light on the sustainment costs. And there's limited data. I know ISBSG has data, but there's very other limited data available for people who want to do estimates based on historical data. So this study uses the ISBSG M&S dataset, August 2020 version 7, 226 data points. So once again, if you look at the paper, you'll see the full extent of filtering that I did for this study, but basically we looked at IFPUG and NESMA data. And we filtered for missing hours. And what I mean by that is that just because there isn't adaptive maintenance hours, if there are hours greater than 0 across the spectrum of maintenance or support, those still could be legitimate data points. So software sustainment is generally considered to be all of the activities associated with software once it has gone into actual production, released for the first time to the public. For the context of this study, because I was using the ISBSG M&S data set, software sustainment from the perspective of my study is considered to be the activities that you see here on the screen. So preventive maintenance, fixing the stuff that you know might go bad, perfective maintenance, adding value, adaptive maintenance, making it continue to work in a situation where the hardware might have changed or the operating system might have changed, and then corrective maintenance, fixing bugs, as well as the stuff that gets done on the support end, investigating problems, answering queries, providing help and help desk support. So what are the questions that we would like to answer with this study? First of all, what can we learn from this data set? So, there's, I want to say, total 1,600 points. As I said, my study only has 227 because I needed to filter it down into a usable chunk. But, so how can we learn to provide estimators guidance to the cost community on estimating the costs of maintenance and support? Are there any useful benchmarks that we can glean from this database that might help estimators in the cost community? And are there any useful cost estimating relationships, CERs, that we can get from this data? So the questions to be answered by this study, those are them. So we talked about the problem. Now we're going to talk about what is the learning process. So the learning process for evaluating a data set. Understand what the data challenges are. Understand and prepare the data. So make the data useful, normalize it, make it all work together. Perform some modeling, and then evaluate the results. And then there's deployment of the solution. And I'm not talking about deployment of the solution today. Once again, there is a much lengthier paper than my half-hour presentation today, if anyone is interested in how we have been working on deploying this solution. So I used the tool, the Rapidminer tool. So I don't know if anyone is aware of this tool. It allows you to do visualization of you drag and drop, creating, if you look at the screen, you can see there's a bunch of operators that do filtering, they do normalization, they do digitization, things like that. So we sucked in the data set into our Rapidminer operator or operations. And we first started by filtering on data points that were either IFPUG or NESMA. And then we went and replaced missing values with zeros where it made sense. So there's a lot of empty fields in the M&S data set. And as I mentioned earlier, sometimes it's not fair to replace a missing value with a zero, but sometimes it is. So if they put in extreme defects, but not unimportant defects, it's okay to turn the unimportant defects to a zero rather than a missing value, because then I can do additional analysis on it. Obviously, there's some things, if they're set to zero, you want to eliminate them from the data set because that doesn't make sense. But in this data set, since there's 7 different values for hour that are collected, it might make sense because some people maybe don't keep track of their preventive or perfective maintenance, but they keep track of their corrective and their adaptive maintenance. So that's going to be useful values that we can use in our analysis. And if I have missing data, I can't do analysis. If I have data equal to 0 hours, some of the hours columns equal to 0. Obviously, in cases where all of the hours were missing, or all of the maintenance and or all of the support hours were missing, then that would be a data point we would eliminate. But in cases where some things were being tracked and some weren't, it made sense to keep those data points. We removed some data elements just based on the age of the data. So we didn't want to go back 15 years. We eliminated a lot of attributes that weren't important to the study, that were deemed not important to the study. And then we did some digitization for some of the qualitative attributes to make it possible for us to potentially do analysis. So at the point where we're doing data understanding and preparation, we don't 100% know what's going to be useful and what's not. We have intuition. I've done this for 300 years, it seems. I think I have a lot of, sort of good common sense, but common sense, and I mean data without common sense is stupid, and common sense without data is also stupid. So, we have to sort of cross that bridge where we want to get the best of both worlds. So the first thing I did after I built this process in Rapidminer is I did a correlation matrix, and this was just, to help me identify the suspects for analysis. So I don't know. Like I said, I have intuition, sometimes pretty good, but you never know. And then we added some operators to the Rapidminer process that I just showed you to not just, so like at the top here, at the top of the screen, you can see my, this is my preparation and understanding phase. Down here, we created, and there were many, many instances of this, and I'm just obviously showing one because it would get really boring if I showed them all. But instances of this where we did specific regression analysis, and we sort of took 2 paths to that. One is we just did a regression analysis, and the other is we did some cross-validation. So we did an analysis just to look at actuals versus estimated based on the regression analysis to come up with some statistics around that. But then we also did a 25-75 split, creating a training set and a scoring set. And we did both of those as part of our analysis. And we compiled a bunch of benchmarks. So if you look here, you can see that, we had extreme defects, minor defects, major defects. So we looked at benchmarks around defects. We also looked at benchmarks around the different labor hours that were being produced out of the, or being provided out of the M&S data set. So corrective, adaptive, preventive, perfective, quick support, user help desk, etc. So we looked at them. We looked at for each of the individual benchmarks that we created, how big was the sample size? What were the min and max? 25, 75% quartiles, mean, median, and the standard deviation and the coefficient of variation. So for each of these things, and this is an eye chart, I apologize, but the idea is we created a bunch of benchmarks. We're looking at things like hours per function point for different activities. We're looking at total defects. So we looked at the totals. No, we did benchmarks for the totals. We did benchmarks for each of the different activities where we had enough data to do benchmarks for those activities. And for each of the defect types where we had enough information to do those. So we created a set of benchmarks out of this data set and tried to make it as transparent as possible. Here's what's good about it. Here's what's bad about it. Sometimes we didn't have as many data points as we would have liked. Sometimes we had more data points. Sometimes we had the whole data set. So here's what we did. And then we did additional benchmark scenarios in cases where we had large enough categorizations. So there were 4 or 5 primary languages that we had enough data points that we could do a good study on. There were several, I want to say 6 application types where we had enough data points that we could do studies that were going to be more focused and going to be more helpful to somebody who is programming in Java or programming in C++. So we did that set of benchmarks as well. And once again, there's a paper, it documents all of these studies. I don't have the time, and it wouldn't be all that interesting to show you those studies right now anyway, but it is available. Anybody that's interested. So with Rapidminer, we mostly did regression analysis, and there were some forays into machine learning kind of algorithms that were less than satisfactory. Not in my mind, I don't know that we had either enough information or the right information, or I think there still needs to be some more learning about the data and how we use the machine learning capability in Rapidminer. We did do some forays into that. They're not ones that I want to present in public because it's a work in progress. But we did, as I said, the cross-validation. So we did a linear regression on the entire data set to come up with some useful metrics about how well data set represents the regression analysis. And we did this, you'll see in a minute. We did it for a bunch of different independent variables. But we also did the split data operator. So we had, we took 25% out to be the scoring set. We saved 75% to be the training set. And we ran that through the linear regression model in order to create a linear regression with the 75% that we then use the 25% and the apply model operator in Rapidminer to validate that. Once again, a little bit of an eye chart, but you can see we had some decent results looking at how defects influence total maintenance hours. Those were our most successful results. We have some other ones that were decent. Application size obviously is going to be a driver, and interestingly enough, more of a driver for support hours than maintenance hours. But so we created a set of CERs, some of which are good, some of which need some work. But once again, transparency. Here's what we did. Here's what we looked at. Here are the results that we had. So I tried to split up my lessons learned into things that we learned that might help people do estimation, and then things that we learned that we might be able to help the ISBSG organization think about how we can improve the data collection process. So certainly in similar domains and projects, support industry-specific benchmarks. Industry-specific benchmarks not nearly as good as some of the ones based on a more detailed focus study. Programming languages, organizational benchmarks, organization type. We also created some rules of thumb to help people figure out a good way to, especially at a ROM point, rough order of magnitude point, figure out a good way to allocate between maintenance and support throughout the life cycle when doing cost estimating. And I think we came up with some good rules of thumb for predicting defects as well. We did come up with some CERs for software support, software maintenance, and program defects. So, there are some CERs, and once again, one needs to look at the data set that we used, IFPUG, NESMA, look at the range of the size of the data set because it's not going to be applicable to everything. But there's some potential useful information there. And interesting finding out of this study was that the relationship around size and defects is better at predicting, in this data set, at predicting support effort than it is at predicting maintenance effort. Which, if one thinks about that, that kind of makes sense. The other observations that, we had as we tried to use this data to help us make reasonable conclusions about support and maintenance costs. First of all, I found that there was a conflict that I have not yet traced down, which is my bad, but not often, there were enough instances of this to disturb me a little bit that the total hours for either support or maintenance, like total hours are listed and then individual hours are listed for the different activities, didn't line up. So this caused a little bit of consternation in my analysis of the data, and consternation that I should follow up on and will. But it's inconsistency in data is a red flag sometimes. Sometimes you just pick a direction. So maybe I'm just going to go with the totals because the totals are the totals. Free form fields are hard to work with when you're doing analysis. And I understand the reason why there's free form fields, but I find it very frustrating, not so much that there are free form fields, but that one can concatenate many different things. So if one's talking about the type of application that they're submitting, it can be like 15 different types of application. And I understand why people might want to do that. I think it would behoove the ISBSG organization to think about ways that we can make that ways that we can make that better so that we can do analysis based on types of applications. I think it would be really useful in a maintenance data set if I was able to not identify the organizations or the applications, but identify organizations and applications that are the same. So there are multiple data entries that potentially came from the same organization or potentially came from the same application, but due to anonymity, that's not obvious to me, the analyst. I think it would be awesome if I could, I don't have to know that it's, unison or IBM or Gallerith, but it would be nice to know that this is organization A1 or application B1. It would be nice to have some sort of anonymous way to align organizations and projects to help maybe fuel analysis. It would be really nice if there was a baseline and then new and enhanced, as opposed to enhancement percent, which seems like it's sort of there but not. Finally, latent defects would be a good attribute to collect, I think. So those are my observations from having to try to do from doing analysis of this data, and I think that it's an incredible, valuable asset to people that want to do analysis of maintenance and support costs, because it's really all that's out there and it's obviously validated and verified. I think there's a few things we could do to maybe make it a little easier to use. And that really is my pitch. I who am standing between some of you and lunch, some of you in happy hour, and probably some of you in your midnight snack. If there's no questions, I'm good.